Yes, students. So in last class, we were talking about energy of wave, right? We got that what is energy, what is the power, what is intensity, all that we calculated. And we got one formula for all of them. Okay. Before that, we were talking about speed of wave in string, right? And we got a formula there also. V equal to root over T by lambda. Okay. But in that case, okay, I'll just give the question, then I'll tell you. Okay. Now suppose that I have a rope instead of a string. Now I have a rope. Okay. Rope is there. Right. Then its mass, you can say its mass is m, length is L. Okay. Mass of rope is m. And the question asks us, find velocity of the wave or speed of the wave at any particular position. Maybe here, at this point, which is at x distance above from the bottom. Okay. Find speed of disturbance at point A. Okay. X distance above the bottom of the rope. X distance above the bottom of the rope. Okay. So in this one, what is happening? Is tension same throughout the string? Answer is no. Tension is not same. In the previous case, when we are solving this, when we got the formula as root over T by lambda, there it was constant. We solved the questions also. We took tension constant. Throughout tension we took same. But here it is not. Reason? Because here tension will be due to the weight of below portion. So here at this point tension will be due to weight of below portion. And now at this moment, what is the weight of below portion? Will not be same when you are going to talk about this point. So at every point, the weight of below portion is changing. So since weight of below portion is changing, tension is different. And if tension is different, speed is different. Okay. So every point, what is different? Speed is different. How to solve? Is formula going to change? No. Formula is same only. What is our formula? V equal to root over T by lambda. That is same. Only thing is we are going to find tension over here. Okay. So who is giving tension here? As I said, weight of below portion. What is weight of below portion? Very simple. Weight of below portion. This portion's mass. This portion's mass is lambda into x. How we know? Because we know that lambda is constant. Lambda is actually m by L also. Lambda is dm by dx also. And same way, lambda is also, suppose this is m1, okay, m1 by x also. Lambda is constant, it's a uniform mass. Mass by corresponding length is constant. If total length I am taking, so total mass by total length. If small I am taking dm and its length is dx, then dm by dx. And if this I am taking, its length is x, okay, so its mass by x is lambda. We know that. So m1 is what? Lambda x. So tension will be what? Tension will be m1g, that is lambda xg. Okay, let's put it over there. So V equal to lambda xg by lambda. cancelled. So V equal to root xg. That means at every position, because wherever you go, you are here, x is something else, here x is something else, here x is something else, here x will be something else. So speed is variable, and answer is what? Root xg. Root xg. Okay? Note that. Are you able to understand, students? Students, are you understanding? So doubt is not coming in your mind. Hmm? Students, doubt is creeping in your mind or not? Then previous questions we did, 2-3 questions we did on velocity. We never talked about this kind of a thing. Here only we are talking. Why? That type of doubt is not coming or coming. If it's not coming, then no problem. If it's coming, then only problem. Is anyone getting that doubt? No one is getting. Okay, then no problem. Okay, now in this one, we add one more question. What question? How much time it take to move from here to here? How much time this disturbance is going to take to move from bottom to the top? Okay, find time taken by disturbance to move to top of rope from bottom. Okay, now one thing we know, that velocities or rather speed is changing, and this is what we got. This is how it's changing. V is equal to root xg. And now what we want? Time. How much is the displacement? L. Okay, from here to here. Displacement is L. Now how to calculate? Displacement by velocity we can do? No, because this is changing. Variable. So what to do? From this velocity only we will be getting the clue. This V is equal to root xg we are writing. What shall we do? This V I am writing as dx by dt, because it's changing. Okay. So dx by dt equal to root x. Then what next? Dx by root x equal to root g to dt. That's all. Done. From where to where? From 0 to L. From here to here. Okay. And time 0 to t. Okay. Note it and give me the answer also. Come on. Note and give me the answer. Done? Yes, students, tell me what's coming. Its integration is 2 root x, am I correct? 0 to L. Here is root g and t. So we are getting it as 2 root L by g. Are you all getting the same? Students, are you all getting the same answer? Yes or no? What happened? Nobody is responding today. Hmm? Students, are you getting the same answer? Okay. So this is how we can find it. Now why we didn't do this in previous questions? Reason was because there our string was very light as compared to the mass you supported on those strings. Compared to that, their masses were very, very less. Something like 0.01 kg per meter or 0.1 kg per meter, and you are hanging here 5 kg mass. So those were negligible. That's why we didn't use it. Okay, but if its mass is considerable, we have to use this. Okay, but normally those questions will not be coming. Either questions will be coming what we did, or directly this question will be asked from you. So don't worry. Okay, done. Right. Now what? I'm going back to intensity. Intensity of wave. We studied intensity of wave formula where we got half rho omega square a square into velocity. Correct or not? But so far, whatever string we have done, question, velocity and all that we have found, in all that we took linear mass density. Here we are writing rho, which is volumetric mass density. So if I convert this formula into linear mass density, then how it will be? Okay, this is intensity. Let's go back to power. Power from here. What is power? Hmm? Intensity is power by area. So power is intensity into area. Hmm? That is half rho omega square a square velocity into s. We took s as area, if you remember. Okay. Now what I am doing? This rho, we know this is mass by volume. Mass by volume. Mass by area into length. Okay. Omega square a square velocity into s. Now this s and this is cancelled. Now it is m by x. So this I am writing as half lambda omega square a square into velocity. Okay, this is power. Now remember this formula also. This is in terms of linear mass density. Okay, this is in terms of volumetric mass density. Okay, note this formula. We'll use this. Done? Completed, students?
Yes, sir.
Okay. Right. So energy part we have done. Now next part in this one is interference. So interference I hope is not required. We should not be discussing. What do you say? Interference we know no. Resultant intensity I1 plus I2 plus 2 root over I1 I2 cos phi. Okay, amplitude is A square equal to A1 square plus A2 square plus 2A1 A2 cos phi. We have done enough questions on that. Shall we skip it? Formula derivation, amplitude, what is maximum intensity to minimum intensity? Those problems you want to do again? Say something. Yes, students.
The same we did in
Which one?
The same we did in wave of
Same. Two waves are interfering. What is going to happen? Intensity will change depending on the phase. Same formula, what we have discussed. Okay, resultant intensity is I1 plus I2 plus 2 root over I1 I2 cos phi. Okay, I maximum is root I1 plus root I2 whole square. I minimum root I1 minus root I2 whole square. Same, everything same, no change at all. Shall I skip this?
Yes, sir.
Everybody? Yes, students, you have to tell me.
Yes, sir.
Okay, so I'm skipping this. Right, then where are we going? We are going to reflection of waves in string. Okay, reflection of waves in string. We all know that waves get reflected. We have studied it in ray optics. Okay, they get reflected. So what is the phenomena that we are going to see? And we are going to see through waves in string. Why? Because that is the way we can see. Okay. So when we talk about reflection, reflection happens from two types of surfaces. Okay. So here how we are showing? We are showing first reflection from fixed end. Reflection from fixed end. Okay. Now try and see what is fixed end here. Okay, this is suppose a pole. And on this pole, we have one string. Okay, this is one string. And it's fixed. Here it is fixed. This is fixed. And this string is tight. It has to be tight, then only the wave will move. Because we know that wave velocity is what? T is not there, then how it will move? T means string is tight. Okay, so string is tight. Now what we are doing? I am going to create one wave over here, disturbance. Half of the wave I am going to create. Half of the wave means what? I will take it up and bring it back to mean position. That's all. I am not going to take it down. Okay. Full pulse is what? Up, then down, and then mean position. Then it will come like this. Okay, but we are creating here half only. Okay, we call it as what? We call it as pulse. So one pulse is created. It's like this. Okay, it goes. It goes in this direction. String is tight only, remember. Okay, so it goes. Now how it goes? Like this. Like this only it is going. Nothing is under that. Okay, so don't think that it will come down. It will go up only. Okay, now what will happen when it is going to reach this part? Okay, when this is going to reach this part. And one more thing, when you are making this is not here. That only is going up. No, that's a string. Okay. What's going to happen when this reach over here? Let's take that part only. Just remove this one here at the moment. Okay. So we are making it like this. This here. What's going to happen? As I told you that string is tight. Okay. If string is tight, that means tension is there. Right? What's happening? Now this string is going to apply force on this particle. This, which is tight. It's going to lift it up. Try to lift it up. Okay? It's applying the force. Which direction? This direction. Which force? Tension. Right? But this is fixed, no. Is it going to move? Answer is no. It will not move because it's fixed. Right? Fine, up to this. But we studied, according to Newton's third law, every action has equal and opposite reaction. So if a rope is or string is going to apply a force on this nail or whatever the fixed thing is, then that nail is also going to apply the force on string. Right? Which direction? What it represents? Every action has equal and opposite reaction. Okay. And now what will happen? Action applied by rope on this fixed end. Fixed end did not move. But when fixed end applied the force on rope, rope moved. Okay. How the force is applied? Down. So what happens to this rope? Came down. It came down. So what happened? What happened is something like this. Okay. All right. Okay. So wave came down and it start moving like this. Okay, because force is applied downwards. So what happened? This came down. Once it came down, then it starts moving like this. This is reflection. One more way is there to explain it. What is there? We studied in ray optics, there is laws of reflection. What are laws of reflection? Angle of incidence and angle of reflection should be equal. Okay, so if I consider this to be normal, then this is angle of incidence. Then this has to be angle of reflection. And both need to be equal. That means this is how the pulse or the wave is approaching the fixed end, and from fixed end it goes in this way. Okay, both ways you can explain. One is every action has equal and opposite reaction because of that force. Okay, comes down, and other one is laws of reflection. What it says, angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. Okay, this is fine. So wave was going like this, then reflected and came like this. But in this one more thing has happened. The phase of the wave has changed by 180 degrees. Phase of the wave has changed by 180 degrees. It was like this. Now it is like this. Okay, it has changed by 180 degrees. Remember that. Okay, the phase of wave or reflected wave. The phase of reflected wave changes by pi radian or 180 degrees. This we discussed in wave optics. This we discussed in wave optics. Okay, but now you can see the proof. Is it clear, students? Any doubt is there? Ask me. Any doubt is there? Yes, sir. Any doubt? Okay. If there is no doubt, please note it fast. Yes, students. Any doubt is there? Please ask. Any doubt? Be vocal. Shall we move ahead then?
Yes, sir.
Okay. Now, when total energy is getting reflected, remember that the amplitude of incident wave and amplitude of reflected wave will be same. Because total energy is reflected, nothing is going the other side. Okay. So, amplitude here and amplitude here is exactly same. Okay. Now, one more thing we should learn in this. Suppose that incident wave equation I am writing as A sine omega t minus kx. Suppose this is incident wave. Then reflected wave equation will be what? Reflection through fixed end. What that will be? A sine omega t minus k to minus x, because it's traveling towards negative x now. Okay, omega t minus k into minus x plus pi, because phase has changed by pi. Okay, what's going to come? Finally, what's going to come? It will come as minus a sine omega t plus kx. Minus a sine omega t plus kx. Absolutely right. Because it has changed. Okay. Minus a sine omega t plus kx. Is that clear? Is it clear, students?
Yes, sir.
Okay. Now, if this is clear, then write if incident waves equation is a sine kx minus omega t, then what will be the equation for reflected wave? Write it fast. What's coming? A sine k minus x minus omega t plus pi. So what we are getting? A sine. Now pi plus something, or pi minus something actually. A sine pi minus kx plus omega t. So A sine kx plus omega t. Is it clear? So these are the reflected wave equations. They can ask you. You should be able to find. Okay. Done, everyone? Is it clear? Yes, students, shall I move ahead? Today you people are very slow. Now what? Reflection from free end. From free end means what now? Free end means this is the pole. Okay. This is pole here. Then it'll make string. String is here. And since it's free end, we'll make like this. It's connected with a ring, which can move up and down, right? But downward motion we are going to block. Should not move down. Only upwards. Okay. So to understand that, now what we are doing, we'll create a pulse here. Here is the pulse. Now this pulse will go, move forward. So when it is going to reach over here, it will be like this. It is like this here now. Now what? Again, when the pulse is moving, that means string is tight. So when string is tight, this is going to apply the force on this ring. Which direction? Upwards. Okay. So apply the force upwards. Now what will happen? Can this move? Yes. Is it light? Very light. Very light. Okay. It's very light. What will happen? You go up. Okay. It will go up. How it will go up? Now next instant, what will happen to this pulse? It will go further up. Rather not up. It will go further in this direction. So it will go like this. Just this link I am making. Okay. It will be like this. This is our ring. Okay. Now what is there? Still this is there. I mean energy in this thing. See, when we say energy in this pulse, energy is there. Energy is there in every part of that. Okay. So what happened in this case? This half is already given. This has gone up. No? Okay. So half energy is already given to this. This is having velocity. Okay. Now further this energy is there. That also will go. Okay. So finally what will happen? This ring will be something like this. Like this. Now no more energy left in the pulse. There is no pulse in fact. All the energy is given to this ring. Right? Now what will happen? Can it go further up? No. Pulse is tight. This is not pulse. String is tight. Now what will happen? Now the string is going to pull it down. There is a tension now here. It's going to come down. So when it's going to come down, it will be same motion, no? Like this. What we did, how we created this. We took it up and then brought it down. Same thing is happening. Here it went up because this pulse has given it energy, it went up. Now, same thing is bringing it down. So it will come down. So when it will come down, it will again give rise to reflected wave. How it will come? We all know that how it will come, right? It will come like this. This is pole again. Okay, and here is ring back to the same point. And then here is the pulse, which will go in this direction. And here is fixed. And this is the reflected wave. Reflected wave from free end. Okay, this is reflected wave. Okay. Previous one was from fixed end. In fixed end, what happened? Phase changes by pi. In this one, is it changing? No. No phase change. No phase change here. Direction is changing? Yes. But phase didn't change. Their phase changed. Here phase did not change. Is it clear, students? Okay, note that. Done? Completed, students? Now suppose in this case incident wave is A sine omega t minus kx. I say you to write the equation of reflected wave. What you will do? Same what we did in the previous case, only thing is we are not going to add pi. Everything else is same. A sine omega t minus k, direction is minus x. So it becomes A sine omega t plus kx. Is it clear? Students, is it clear?
Yes, sir.
Okay. Let's try and see. I thought that I'll show you a video. Possibly, let's see if we can play it. If we can play, let's see. It's not showing from here. Okay, we'll go through other way. Where it is? Yeah, this one. Right. See that? Okay. This is fixed end. See how it's changing. Same thing that we discussed. Okay. This is reflected one from fixed end. This is free end. And this is the ring. See this one, how much up it is going. Not only this, it will go further up. Okay. See. Because it has to give entire energy. Okay. So this is how reflection happens from fixed end and free end. And I told you what are the equations also. Right? Are you able to see? Is it clear to you?
Yes, sir.
Okay. How to take it back now? Okay. Right. So this is how reflection and reflection, both are reflection, there is no refraction. Okay. Reflection happens from fixed end and free end. Reality also like this is going to happen. Something like fix is going to come, may come, but most of the time it will not be there. Then it will be like this. There will be one string. This is one string. Okay. In this one, we are generating, let's say, pulse. And now here it is connected with another string. Another string which is maybe some other string which is heavier. Okay. Like this it will be. I'll make it in a proper way. Okay. So one string is like this. Okay. Another string we will make. Another string from here. Okay. And we'll show it in a different way. Like this it is. There are two strings are there. Okay. But their mass densities are different. Okay. What is different? Their mass densities are different. This is string 1. This is string 2. Okay. This is mass density is lambda 1 and its mass density is lambda 2. If lambda 2 happens to be more than lambda 1 and you have created pulse over here. Okay, this is how we have created the pulse. Then we will say that wave is moving from rarer to denser medium. Wave is moving from rarer to denser medium. Then this junction here, this is a junction. This junction is going to act like a fixed end. It will be similar to fixed end, not exactly fixed end. Okay. It is similar to fixed end. Similar to fixed end. What is going to happen? See now, I'm just showing you. This pulse is going to reach here. Okay. Now, if it's similar to fixed end, that means there will be reflected one, reflected pulse also. Yes, reflected pulse will be there. This is reflected pulse. This is reflected. But at the same time, there will be transmitted pulse also. Because this is not fixed. It's not fixed. Fixed there was what? In which energy cannot be transferred. Okay. It has to fully reflect back. But here it's not like that. This is also a medium. There also energy can go. Okay. So this is reflected and then there will be transmitted one also. So this is transmitted. Transmitted pulse. This is reflected pulse. When you are going from rarer to denser medium, then this is the case. In this case, what will happen? If suppose this is AI, then this is AR and this is AT. Denser to rarer medium. So this time, what he'll do, we'll make two strings first. This is string number 1 and let's take its clone itself. Okay, and color it. Okay. Right. Just like this. Now this time lambda 1 is more. This is lambda 1 and this is lambda 2. So we are saying lambda 1 is more than lambda 2. That means our first string is more denser than than second one, then second string. Okay, so this junction here will not act like a fixed end, it will act like a free end. When you go from denser to rarer, it acts like a free end. When you move from rarer to denser, it acts like a fixed end. Here it is what? Free. So again, let's create the pulse. Here we created the pulse. It's going like this. Okay, so it's going from denser to rarer. This is junction. This junction is similar to free end. Okay, what's going to happen? See, this will reach over here. Okay, now transmission is also going to happen, reflection is also going to happen. So see then, how is transmission? This is transmission. Okay, then reflection. Here is reflection. This is reflection. Okay, because this acts like a free end, there is no phase change. In the previous case, there was phase change for reflected wave. Here there is no phase change. And for transmission, there is never a phase change. Okay, for transmission wave or for transmitted wave, there is no phase change. From any type of boundary, okay, from any type of junction. Talk about what is the relation between the power of incident wave, power of transmitted wave and power of reflected wave. Okay, so relation says that power of incident wave is equal to power of reflected one plus power of transmitted one. Okay, this relation is valid. If we consider that there is no power loss, then Pi equal to Pr plus Pt. Remember that. And what is power formula? Already I told you. 1 by 2 lambda omega square A square velocity. Okay, 1 by 2 lambda omega square A square velocity. Clear? Then we should also know that how to find the amplitudes of reflected and transmitted wave. Okay, for that also some formulas are there that you have to remember. Okay, so what is amplitude of reflected one? It is V2 minus V1 by V1 plus V2 into amplitude of incident one. And AT is what? 2V2 by V1 plus V2 into AI. Okay, note this formula, then you solve a question on that. Okay, note this formula. Completed?
Yes, sir.
Okay. So now suppose that we have a question in which two strings are there. Okay. Two strings are there like this. This string 1 and string 2. Okay. Lambda 2 is actually 4 times lambda 1. That's given to you. Okay. So incident wave, I am making as A sine omega t minus kx. This is my incident wave. Okay. Now what you have to do? You have to write equations of transmitted and reflected wave pulse. Okay, you have to write equation of transmitted and reflected wave pulse. Simple question. Lambda 2 equal to 4 lambda 1. Okay, come on. How are we going to write it? Let's see. Note that first. Completed? Done?
Yes,
Okay. So how the wave is going? It's going from medium 1 to medium 2. Obviously, that is only we do normally. Here is your pulse. It's moving from medium 1 to medium 2. Right? Question is saying that write equation of transmitted wave. Now, equation of transmitted wave will be what? We'll write it as yt equal to at sine omega t minus kx only. Because we know that transmitted wave and no change in phase. It will have it the same way. It will travel in the same way. So, only thing I have to find here is AT value. And AT value is formula. AT's formula I know. What is that? It says 2V2 by V1 plus V2 into amplitude of incident one. Okay, fine. Now both the strings are connected. Okay, So if tension here is T1, junction we are talking. Here is T1 and here tension I take as T2. Okay, and suppose T1 is greater than T2. What's going to happen? This junction will be pulled in this direction, right? And if T2 is greater than T1, then junction will be pulled in that direction. Yes or no? That means string is not at rest. That does not happen. Okay, junction will always be at rest. When can it be at rest? When T1 is equal to T2. So remember that at junction, tension in both the strings will be same. Point number 1. Now let's talk about velocities. Why? Because velocities only we are bothered about velocities only. Okay, so here if suppose I say velocity of this is v1 or v, shall I take? V will take, okay. V. So velocity is v. So what is v actually? V actually is root over t1 by lambda 1. Correct. Then velocity in this one, if I make over here transmitted one, its velocity is, let's say, v2. What is v2? v2 is root over t1 by lambda 2. So can we have a relation? Yeah, obviously, because lambda 2 is 4 lambda 1. Okay, so this one v2 I can write as t1 by 4 lambda 1. That means this v2 is actually what? v2 is t1 by lambda 1, root 2 over t1 by lambda 1. We can write as what? V. See, have I written correct or not? Root over t1 by lambda 1 is v. So here also root over t1 by lambda 1 is v by root 4. And that means v2 is equal to what? V by 2. Okay, we got the relation between v2 and v. Now we can put it in this one. What is 80? 2v2. So 2 into v by 2 by v plus v by 2 into a. Okay, what we are getting? This 2 and 2 gets cancelled first. V by 3v by 2. 3v by 2 means 2 will go up. So 2v by 3v into a. That means 2 by 3a. Transmitted wave's amplitude is 2 by 3. So we can write this as 2 by 3a sine omega t minus kx. Okay. This is your incident wave pulse. Right. Note this one and then try to find reflected one. Come on. Any doubts, students? Any type of doubt? Yes, students, any doubt is there? Okay, note that. Done? Okay, let's find reflected one then. What will be the case with the reflected one? First, let's write its equation. Okay, before that, we should know that whether it is from denser medium or rarer medium, from where it is getting reflected. You say that 1 to 2. 2 is only denser. Okay, so it's trying to enter from rarer medium to denser medium. That means it will act like a fixed end. That means pulse will be having a phase change of pi. Okay, so remember that. So reflected wave. So reflected pulse we'll be writing as AR sine of omega t minus k into minus x plus pi. Right? Then now it will be written as AR sine of omega t plus kx plus pi. So it will come as minus AR sine omega t plus kx. Now question is, what is AR? Okay, so AR formula is V2 minus V1 by V1 plus V2 into AI. Correct? So what we are getting? V2 is what? V by 2 minus V by 3 by 2V into A. Okay, so what we are getting? This is minus V by 2 by 3V by 2 into A. Correct only I have done? Check.
Yes, sir.
Okay, so what we are getting? V by 2 we can cancel as minus A by 3. This is AR value. Okay, minus A by 3 is just showing that it is below, down. Okay, nothing else. So we'll put it over here, A by 3. Right? So A by 3 sine of omega t plus kx. That will be a reflected waves equation. Now, can we prove in this one Pi equal to PR plus PT? That also we can check. Okay. Pi equal to PR plus PT. Or rather, let's write individually what is Pi. What we studied 1 by lambda, 1 by 2. I am writing 1 by 2. 1 by 2 is there, no? Half rho. Yes, half is there. I got confused. 1 by 2 lambda omega square A square into velocity. This is incident wave. Okay. Reflected one is what? Reflected one I am writing. Reflected one is again in the same string in which incident one was there. Okay. What is different? Only A is different. Remaining all are same. 1 by 2 lambda omega square is same. A has become A by 3. V is V only. Perfect. Transmitted one by 2. Now lambda is how much? I think 4 times lambda, right? So 4 times. 4 times lambda. Omega is same because frequency doesn't change. When energy goes from one medium to other medium, which property remains same? Frequency. Remember that. In light also we discussed, here also. Okay. So when energy moves from one medium to other medium, frequency remains same. So omega is same. Amplitude 2A by 3. Speed V by 2. Okay. Now if these two I am going to add, this should come. Check. Are we going to get that? So here is a square by 9, and here is what? 1 by 2, let it be here. So this is, we have to check, 1 by 2, this and this gets cancelled. So this is 2 lambda omega square, this is 4a square by 9. So 8a square by 9 plus a square by 9, yes, pi is equal to pr plus pt, absolutely. Is it clear, students? Students, is it clear?
Yes, sir.
Yes, sir.
Okay, note that, because sometimes they will ask you like this, they will give you this power, okay, and they will give you some methods so that you can calculate at least one of them, and they will ask you the other one. So directly apply this one and solve it. No need to go for this method. Okay, note it. Completed, students?
Yes, sir.
Okay, so this is reflected and transmitted we saw. Now in the next class, we are going to see standing waves. Okay? Alright then, see you in the next class. Bye-bye.
Thank you, sir.